extraction objective is to distill nitrogen from air. Atmospheric air contains multiple impurities such as carbon dioxide and water, which can be harmful for equipment downstream. That's why these components should be eliminated before the distillation column through a phase separator and an adsorption column. HYSYS cannot simulate adsorption columns, so instead there is a component splitter. Then air is compressed up to 40 atmospheres in 2 steps. To efficiently reach the cold needed for the cryogenic distillation, the feed to the column should be pre-chilled. Through an energy integration, it is possible to use the cold from the outlet streams from the distillation column to pre-chill the feed to the column. It is important to do correctly the mass balances on these component splitters so the temperatures do not cross in the heat exchangers. For the distillation column, we followed a simple Linde column design. To ensure that the purity of the nitrogen current is enough for the ammonia synthesis, part of the head product should be recycled to the top of the column. In this case, this current should be compressed, cooled, and expanded again. In reality, this current would be put in contact with the reboiler, so an adjust is used to ensure that both duties have the same value. At the end of this section, we obtain two oxygen current, one liquid, another one gas, and a gas-nitrogen current, which will enter section 3.
The second section focuses on hydrogen production through supercritical water gasification of forest biomass. A key challenge was modeling the eucalyptus residues, which we define as a hypothetical component based on elemental analysis and its heating values. To address potential fouling and energy issues, our design, as seen in the diagram, pumps and preheats the water stream separately before it meets the biomass at the reactor entrance, ensuring the heat exchangers handle only clean fluids. We use the Penn-Robinson equation of state to accurately predict phase behavior at the supercritical condition of water, 240 bars and 700 Celsius degrees. The gasification is simulated in a two-stage sequence. In the first, reactor handles the primary elemental thermal decomposition, and the second reactor calculates the chemical equilibrium where we optimize the water-gas reaction to maximize hydrogen selectivity. This heat exchanger recovers heat from the hot products to preheat the incoming water, reducing external thermal demand. Finally, in the separation section, we obtain a high-purity hydrogen stream. In other part, our process maintains a pure water recycle, closing the loop and ensuring both technical and environmental sustainability of the plant.
The first section covers the core of our green ammonia process, the synthesis loop. To handle this high-pressure chemical system accurately, we implement the Penn-Robinson Strayed-Vera equation of state. For the reaction, we model the Temkin-Fishev equation, but because of its complexity, we configure a customized kinetic expression in HYSYS. We use a Temkin factor of 0.5, resulting in fractional reaction orders of 0.5 for nitrogen and 1.5 for hydrogen. This accurately simulates the inhibition effect of ammonia on the catalyst surface. Synthesis requires 200 atmospheres, so we design a 5-stage compression drain with a 2.75 compression ratio per stage to keep discharge temperatures below 150 Celsius degrees, protecting mechanical integrity. Interstage cooling to 20 degrees significantly reduced the total compression work. Notice the integration of high and low pressure recycles directly into the drain to maximize efficiency and reduce capex. The synthesis is carried out in 3 adiabatic bulk flow reactors in series. By using 100 cements per reactor, we obtain a precise composition and temperature profiles. Look at the temperature curves. The reaction is highly exothermic and reversible. We implement intermediate cooling via high-pressure steam generation to move the mixture away from the equilibrium curve and maintain maximum reaction rates. Product recovery is achieved through a 2-stage flash system. The high-pressure separator at -5 degrees Celsius recovers reactants, while the low-pressure stage at 20 bar degases solubles to reach a final purity of 99.87%.